Leader-based sequence Paxos. We will introduce a leader among the set of proposers. Any proposed command is forwarded to the leader. As we will see, this allows correctness-preserving transformation of the vanilla sequence Paxos algorithm. In the resulting algorithms, proposals can be pipelined asynchronously, and most proposals will take one round trip with minimal contention under good network condition. The first thing to do now is to develop a new leader election algorithm that is suitable for sequence Paxos. Let us look to the problems with the current algorithm. The previous algorithm presented satisfies all the safety property, but we may not make progress. So a proposer can run only one proposer until decide before taking the next proposer. So it means we do not have pipelining of proposals. And the second problem is that multiple proposals may lead to live flocks. For example, having multiple proposals simultaneously and they will run over each other. And as we have seen, 2 round trips will be needed for each sequence chosen. These 3 problems will be solved by electing a leader. We'll still have other problems like entire sequences are sent back and forth, and all the variables, the sequence at the proposal, the sequence at the acceptor, and the sequence at the learner are mostly redundant. These 2 other problems we will solve later. So what is our assumption here? We assume an eventual leader election abstraction, and that means that we are in the partially synchronous model. But this leader election abstraction is a bit different than the omega abstraction that we had previously. We call it a ballot-based leader abstraction. So a leader will come not only by saying, I am a leader, by this indication, but it also comes with a round number or a proposal number. The ballot-based leader election satisfies completeness and eventual accuracy, but also it is going to have a monotonically unique ballots that increases every time I elect a new leader. And the leader-based sequence Paxos will be optimized in the case of a single proposer that runs for a longer period of times as a leader, and thus it will not be aborted for a while, but it has to guarantee safety if aborted. So here is the properties of our leader election abstraction. We elect a leader with a ballot number n. This says that Pi is a leader with a ballot number n. And the properties are the following. Completeness, which says eventually every correct process elects some correct process if a majority of processes are correct. We add this extra requirement because anyway, in a Paxos algorithm, if majority are not correct, the algorithm will not proceed. The second property is eventual agreement, which says no 2 correct processes elect different correct processes. So eventual agreement one more time. Eventually, when timings is correct, all correct processes will elect the same leader. The third property, which is a new property here, which is unique and monotonic ballots. What is it? It says if a process L with a ballot N is elected as a leader by process Pi, we now just look into the view of process Pi, then all previously elected leaders by Pi have ballot numbers less than n. And also, the combination, which is the leader with the ballot number, is unique. This combination is unique, so that we don't have leaders having the same ballot number. Given this, let us just illustrate this a little bit. So we say that ballot leader election elects a leader L with higher ballot number n than all previous leaders L prime. So here we have a situation which we say that if a process P elects a leader, and this is the view at P, then all previously elected leaders with L prime, N prime at P will be the case that N prime should be less than N, and the pair, all the pairs, L prime, N prime, are unique. This is illustrated in the following example. If we look to the execution or a trace, these are the processes, and this is time. So we have a situation where P1 first elects P3 with ballot number N1. The same thing happens here, and the same things happen here. Now at this point, P3 dies. So P1 elects itself with a ballot number N2, and now it considers itself as a leader, whereas P2 still considers P3 as a leader. Then P1 elects another leader, which is P2, with ballot number N3, and in this case, N1 is less than N2 and is less than N3. P2 still thinks that P3 is the leader, but at this point we come to an agreement, whereas then P1 elects itself with ballot number N4, and P2 elects also P1 with ballot number N4. So here we have an agreement, and N4 is the largest number. It's larger than N3, N2, and N1. So given we have now a leader, we can look to the state of the proposers in sequence Paxos. So we still have a set of proposers, and among them one be elected a leader, and any proposer can either be in a leader state, this is the one, or a follower state. And once a process or a proposer is elected, he might be first initially in a prepare state, and later he will go to an accept state, and he will stay as a leader until overrun by a leader with a higher ballot number. In this case, he will move to become a follower again.